Hello again, everyone. This is a little quick lesson here for photoelectron spectroscopy. This is one of those topics that they sort of added to the AP curriculum, and they do test on it, mostly because the guy who used to be in charge did his graduate research in this, and I think he just kind of forced it on us. It's sort of helpful. At the high school level, I'm not sure how helpful it is, but it can be used to help you understand ionization energies and electron structure somewhat. So again, it's photoelectron spectroscopy. We're going to call it PES for short. We can use it to understand structure, electron configurations, ionization energies, and where we come up with those numbers, and then eventually, of course, periodic trends. Now, to understand how PES works, we need to think back to the Bohr model. And the main part of the Bohr model that we need to remember is that these electrons are in these fixed shells. Okay, so they have a set amount of energy, and being on level 2 here, for example, means an electron has that much energy. Okay, if you were to put energy into the atom, let's say shine a UV lamp at it, then the electron will absorb the energy, and then it will become energized and go up to these higher energy states. So we talked about that, and we talked about how far it rises depends on the wavelength or the frequency of the incoming photons. In this example here, it's a red photon, and it only went up from level 2 to 3. And then we also talked about how when the electrons are in this excited state, they don't really want to be there, so they will eventually fall back down to a lower state. They don't have to go all the way to 1, just wherever they were excited from, or wherever there's an open spot, they'll fall back down, and then they will give that energy, that extra energy they had, off in some form of a photon. So that idea from the Bohr model is very important in understanding PES. So what is it? It's a high energy laser or EMR source, and we're going to shine it at a sample of matter. And since we're using UV or X-rays, usually X-rays will guarantee the electron to come off. Most of the time it's X-rays, but if it's in metal especially, you can get away with UV. And so you eject an electron from an atom, and it will be a very specific energy. Now, since electrons within an atom are in different energy levels, the different electrons are going to require different amounts of energy to eject. And we have to remember that the ones that are harder to remove will be the ones that are closest to the nucleus. They're closest to that positive charge. And Coulomb's law tells us that the closer you are, then the harder your force, the larger your force is going to be, the force of attraction is going to be. So the electrons that are closest to the nucleus are going to be harder to remove. And then the valence electrons, which are by definition the furthest out, are going to be the easiest electrons to remove. So what this thing does is put enough energy into the atom so that you can remove almost all of the electrons, or there's so many atoms there that just through pure statistics, you will get electrons from all levels being emitted, and you can see those register on the graph. Here's the experimental setup here. In this one, it's a silicon oxide sample, so we're looking at silicon here. And this cone here shows you this is an X-ray source. So X-rays are going to shine on this sample of silicon, and then electrons are going to be excited. They're going to jump up here. Now if you look at the very bottom of the screen, I can't go highlight it because the little box will come up, but it says samples are usually solid because XPS requires ultra-high vacuum. Why do you think there has to be a vacuum there? Well, the vacuum has to be there because these electrons are being kicked off and they're traveling to the detector. If the vacuum weren't there, then those electrons would hit molecules or atoms of air, of oxygen and nitrogen and argon, and they would be deflected and never get to the detector. So you have to have a vacuum there purely for travel's sake. So here we have the electrons. It's going to be collected through this lens, and then it gets sent down to the detector, and eventually we'll get a printout of the number of electrons coming out of certain energy values. Okay, so here is sort of a little equation to explain what happens. So we know how much energy we're putting in from the photons. And then so it's going to hit the atom, and then we're going to get an electron removed. It's going to be a cation because we're taking away electrons. And then we can also measure how fast the electrons are moving when they come off, how much kinetic energy they have. Because if I put an X-ray onto a valence electron of, say, potassium, it's going to come off very fast because only a small amount of energy was needed to get it to remove it. And all that extra energy from the X-ray just goes toward making that electron move faster. But if it's an electron in potassium closer to the nucleus, let's say on the first energy level, then the X-ray will have enough energy in it to kick the electron out, but it took a lot more energy to do it. So there's less leftover energy for the electron to be traveling very fast. The detector is also able to detect that and sort of pinpoint where the electron came from. The output looks something like this. On the y-axis, the main thing is its intensity. It's how many electrons had that energy. So it could either be a set number, like 1, 2, 3, 4, 5, 6, or so on, or it could just be a relative number. So you would like set the lowest peak as your base, and then the relative heights of the peak would be all you looked at. On the x-axis, you have some sort of energy. That's the main thing, some sort of energy. I want to point out that the x-axis is numbered backwards, and there's a couple of ways to do this. So this is not like a national or international standard way to do it, but this is the way you'll see it on the AP test. That's been decided. They write it backwards because the theory is the first electron that comes off is going to have the highest energy. So you'll see your peaks over here. Those would be your first energy level. And so they want the printout to be first energy level electrons here, and then we'll see a couple of peaks for the second energy level, and then you'll see 3 peaks for D, and so forth. So just make sure you pay attention to the x-axis and the direction it goes all the time. Here's some sample graphs. So here's a very good printout. So we see here the highest energy electron, the binding energy. So we would say this is the first energy level, and then out here I see a grouping of 2, and we've learned from our electron configurations that the second energy level can hold S's and P's, and that's what we're seeing here. And then over here we see another cluster, so this would be probably the third energy level. You can also see the heights and how the heights work relative to each other. If we can kind of count this peak, we know this is the second energy level, and probably the S, we can go up. There's 2 lines here, and then we can count up 1, 2, 3, 4, 5, 6. So here we can see that this one is on line 6, this one's on line 2, or if you look at it relative to each other, this one's on line 2, 6, so that's 3 times bigger, or 3 times as many electrons. Either way you count it, there's 2 electrons, 2, 6, so that is 10, 12, and then here we see 13. So that means this is the PES output for aluminum. All right, and then we can see again at the bottom, I'm not going to be able to use my pointer apparently, but we can see that we have on the far left a single peak, that's 1s2, and then we can see a grouping of 2, that's 2s2, 2p6, and then we can go down, we can see 3s2, 3p6, and then we can see some noise over there for some 3D electrons. All right, so let's see if you can do this. So what element would you think this would be? Yeah, so the height here is like 2 electrons, so most likely this is going to be helium. All right, which element do you think this is going to be? All right, so we got 2, 4, 10, 12, and then 3 more. So this is going to be 15 electrons. I don't have my periodic table handy, but I believe that's phosphorus. A real spectra is not quite as nice and tidy as what we'll see on our printouts. It has this kind of a rough curve to it, but in the end, you can still measure the relative peaks. So for real spectra, relative peaks are going to be a lot easier to do than just looking over at the y-axis. And then finally, let's end this up. This is last year's AP exam, 2018, and this is the exact question they got. And number 7 says the complete photoelectron spectrum of an element is represented above. A, identify the element. It was a very high scoring question, so take a moment. What element do you think that is? Hit pause if you need to. Alright, you've had time to think about it, so we look at it. There's 2. These are the same heights, so we'll say 2, 4, and then this one is only slightly higher. Okay, so this is not going to be a full P. It looks like there's only about 3 electrons here, so that's going to be 2, 4, plus 3 is 7, and I think nitrogen was the right answer to this, so 7 electrons. So that's it. It's not very difficult. We'll do a little in-class practice as warm-up, but that's it, PES.